So as you are all aware, this course is about optimization. So we'll first get into like the general structure of the course. So I had mentioned this already in Moodle. If you check the announcements, you would have seen that. So I've talked about the grading scheme and the textbooks we'll be following. So let me again refresh your memory on that. So grading scheme will be as follows. So assignments, like almost every week, like maybe we'll miss once in a while, but almost every week you should expect an assignment, which will be due in about a week. So that will be about 30% of your grade. So that will be assignments. And then somewhat like a mid-sem, there will be 20%. So take home mid-sem, in the sense it will be essentially an assignment, but instead of having a week, you will have like a day. So take home exam. And then third, of course, 50% will be a final exam. And based on this, and most of them will be theoretical. In the final exam, I have mentioned, but in the assignments, we'll have a little bit of programming part. As optimization, of course, one can learn the theory, but a bigger portion of that, when you try in practice, has to do with like optimizing efficient algorithms, like how it works out in practice. So for those, I will be using certain Python modules like CVX, opt, convex optimization, those kind of things. But anyway, I'll give tutorials and Jupyter notebooks for that. So no worries if you have no familiarity with Python. And let me ask a quick question. Have you done a programming course before? Like in your first year? I guess not. Like probably the C programming
Yeah,
is.
sir, we did it in C.
So you did that already in your first year, right?
Yeah, in C language.
Okay, okay. Yeah, I mean, Python is much easier than C. It shouldn't take you
Yeah.
much. It's an interpreted language, unlike C, which is compiled. So it's much easier to learn. But in any case, I'll like run you through the basic things. But yeah, but in the exams, you will not have any. You will not have to submit any code, those kind of things. So exams will be primarily theoretical. Um, and I already mentioned that the main book we'll be following is the book called Convex Optimization. Uh, by Boyd, and let me just check. The second name is a bit hard to remember. Vandenberger. So this is freely available, so you can just download it and use it. And this is actually somewhat of an advanced textbook. So in that sense, I would say that just try to follow the lecture notes. I will be posting this like the hand scribed notes, which I'm writing now on my website and also on Moodle, and also these videos. So that should be good enough for your exams and assignments and so on. But if you really want to read ahead and like gain a very strong mastery over the subject, you can go ahead and read this textbook on your own pace, at your own pace and time. All right, and for the simplex, like the linear programming part, we'll be following this book called Linear Programming by Howard Karloff. And I also mentioned a third book called Algorithms for Optimization, but we'll be like very, um, in a sense, like we'll be using it in a very rudimentary sense, not. It will just be a reference rather than being a textbook. So these will be the two main textbooks we'll be using. But if you follow the lecture and like the lecture note, that should be good enough. All right. So do you have any questions about the general structure of the course?
No, sir.
Okay. So yeah, if not, then we'll get into brass tacks. All right. So anytime we have a course in mathematics, typically there is a theme. There is a thematic question we want to answer. If you learn linear algebra, it's about like solving linear equations, and it can start with very simple ideas, but slowly, as you get into the details, it becomes like more and more complicated, and you start appreciating the terrain more and more. So here also, what is the thematic question for this course? So we'll phrase it in very vague terms and slowly mathematize that question. So what is the thematic question? So in a particular situation, whatever that is, with examples, of course, this will be clear what this means. What is the best decision or choice best decision or choice towards a particular objective. So at any point in the course, if you're left wondering what exactly are we doing, come back to this question. And then let's like ruminate a little bit over what these words mean. Like, of course, this is a pretty vague statement. For a mathematician, this is not something they can work with. So we're saying an adjective like best, decision towards a particular objective. So here, when we say decision, that means we have a bunch of choices to make, candidate choices. So these are, let's call them candidate choices. So I'm representing them by points. And I'm saying something like best. Amongst these, I have a measure of goodness. So if I want to say about, I want to talk about best choice, I need to have a measure of goodness. And if I want to like talk mathematically, I want to be able to compare these choices. So if this is a choice, and I'm making a decision. Making a decision means making a choice of like, what do I want amongst these? So then I want to compare these choices. So this measure of goodness is essentially comparing these. And there is an objective. So you have certain goal in mind, like maybe like you want something like good, or maybe perhaps you want something really bad. So what is your objective? It depends on that. So based on this question and this mathematization of these words, the way we'll phrase this is we have a space of candidate choices. So here, if there are finitely many choices, then you just have some discrete points. But it could be like something more complicated. We'll get to, once we get to examples, we'll identify what space of candidate choices looks like and what this measure of goodness looks like. But right now, let's be a little bit vague and to allow for generality. And then there is something, by the way, this is sometimes also known as a decision space. So these are all the options that you have. And then there is something known as an objective function on the space of choices, on the decision space. So what does an objective function do? It takes a point, like it takes a choice, and it gives you a number out of it. And that is the measure of goodness. So if the number is higher, then it is better for your purpose, towards your objective. That's why it's called an objective function. So, and of course, like depending on what specific goals you have, like for example, you want to talk about choices where you are making more profits and these kind of things. So sometimes those are known as cost functions. But yeah, objective functions are the more generic term. So if you want to put it this way, it has to be like, you have to pay a price for any given choice. You have to pay a price. You can interpret this pay a price in like in a literal sense, or in a sense of a phrase, to pay a price, sometimes literally, for any given choice you make. And you want to make the best decision. All right. So this brings us to what an optimization problem typically looks like. So when you want to say best, that always means that you're trying to optimize. You are trying to find like something which is the best suited for your objective. Okay. So essentially, any optimization problems will have two components, which we have already described, but let's note down so that like it is concretely there in our heads. So essentially, any optimization problem will have two components. Has two components. So one is a decision space, which let me denote by X for now. That X can be many things. The reason I'm talking this generally is because in the examples I'll show, X can be many things. It doesn't just have to be some sort of, perhaps if you have read ahead and you know a little bit about optimization, you might have this impression, okay, we have these inequality constraints and it looks like something in Euclidean space. It doesn't have to be interpreted that way all the time. So we'll see that through examples, but in general, just think of it, there is a decision space X, and then there is an objective function F on the decision space, function F from X to say R. It could be any totally ordered set. For totally ordered, because I want to be able to compare any two values. So I choose a point in X, that is one of the decisions that could have been made or one of the choices. And I want to say whether Fx is better than Fy. So this target space or the codomain better be something which is totally ordered. But so for us, it will be any subset of R will suffice. Like sometimes we will take R plus, like positive real numbers or non-negative real numbers, these kind of things. So as long as we're able to compare any two numbers, we're fine. Like if you want, you could also take matrices, but or complex numbers, but it would not be that useful, like for this in the sense of optimization, but because there's no like clear way of comparing to complex numbers. So that's why we'll just stick with real numbers. Okay. So objective function f taking values in R. So these are the two things. And what does an optimization problem look like? So essentially you have to maximize or minimize f on this decision space. So I'll just write minimize f, but maximize, you can imagine this is R, or like if your codomain is R, you can always talk about maximizing minus f. So minimizing f, the general nature of the problem will be the same as maximizing minus f. So we'll just stick with one of them, and it will be implicitly understood that the other can be just solved by changing the sign of f. And the second problem is, so minimize f meaning find the minimum value of f. And the second problem, which is typically what you want, is argmin. Argmin meaning which choice, so this is the decision space, which decision actually minimizes f. So that is the value of x which minimizes f. In fact, this is typically the harder problem. So any optimization problem will typically look like this. Then when we look at the specifics, we will talk about, okay, how do we like in fact specify x, like through inequality constraints and so on. But in general, you should think of x as just being some space, like some set with perhaps some extra structure depending on the problem. All right, so now we'll be a bit even more concrete. So often the decision space is described using constant functions. Perhaps I'll change my color here. So often the decision space is described using constraint functions. So just like we had an objective function, I said there are two things, objective function and decision space. So you could have replaced one in this particular case by saying, okay, we need two things. We need objective functions and constraint functions. Yeah, so constraint functions, what do they do? So these constraint functions involving decision variables. All right, so here you have the following problem. I'll define the notation, but for now, let me just state it. Minimize f naught x subject to the following constraints. So minimize this objective function subject to fi x less than equal to bi, I equals 1 through m. So there are m constant functions. So this is the optimization problem. So let me call this OP. All right, and here this is actually 0. I want to say this is 0, but at the same time, if you read this as O, nothing is lost because f0 is supposed to represent the objective function. Okay, so what is x? X is x1 through xn, so it is an element of Rn. And you can think of these as the decision variables. So each of these components, you can think of as certain decision variables. So, and all this terminology typically comes from the like real world problems you're working. So mathematically, you can just think of it as some vector in Rn, some element of Rn. Yeah, and f0 is a map from Rn to R. So this is the objective function, which is what you want to minimize or optimize. And these FIs are constraint functions. They're essentially telling that it's not that we care about the whole of Rn, arbitrary vectors, but only those vectors which satisfy this condition right here, fi of x less than equal to bi. So these are the constraint functions. And this whole thing determines decision space. I'm always coming back to that description that you need two things, decision space and objective function. Okay. Yeah, and this B1, B through Bm, you can just say these are the bounds. B1 through Bm are the bounds for this constraint function. That is kind of understood. All right. And a vector will be called optimal. So vector x star, this is just a matter of definition. So it's called optimal, or a solution of OP2, of OP, or a solution of OP. That is the optimization problem, the description that we had given right here. If it has the smallest objective score. You can call it objective score or object like value of the objective function. But all this terminology are supposed to be suggestive of like what the purpose of like framing and solving these problems are. Okay. So yeah, if it has the smallest objective score among all vectors satisfying the constraints. Among all vectors satisfying the constraints. That is amongst for any z. So constraints meaning for any z with f1 of z is less than or equal to b1 all the way up to fm of z less than or equal to bm. And yeah, so for any such z, we have f naught of z is bigger than or equal to f naught of x star. This is just rewriting mathematically what is said here. A vector x star is called optimal if it has the smallest objective score among all vectors satisfying the constraints. So mathematically, how do we say that? That for any z satisfying this constraint, that is that z is in the decision space, you have f naught of z is bigger than or equal to f naught of x star. All right. So now we have framed the problem, the general problem we want to solve. Now that there are two components, so depending on the nature of these components, like for example, I could demand that my space of functions or objective function is linear, and at the same time, these FIs are also given by some like linear functions, like these constraint functions are given by linear. Then I'll get a class of optimization problems. Or I could choose f naught to be certain like smooth functions and fi to be like perhaps this inequality is in fact actually an equality. The sphere is such an example. So you're trying to solve certain optimization problems on the sphere, which is like a smooth manifold. So depending on how you vary like your decision space, the decision space could be discrete. So then it is much easier in the sense it is mostly a matter of sorting, right? In C, since you have done a programming class in C, you have probably seen different sorting algorithms. So if the decision space were like a discrete space, then it is a matter of just finding this, evaluating this objective function at each of those points. So now let's say that x had n points. So let's say x is discrete space and has n points. Space having n points. So then like you have f0, x1 and f0, xn. So it's just a matter of sorting these. And then you have all this complexity analysis of how like in terms of both time and memory, like how can you do this, quick sort and so on. So here at least you know that the problem, there is an algorithm to do this, to solve this problem. And of course you cannot just have a simple mathematical theorem saying that, okay, there exists a solution. So here the existence part is actually much easier to see. I mean, it's finitely many numbers, there has to be a maximum and a minimum. So existence and those kind of things are pretty easy to see. Actually finding it is the harder part, and that we know how to do. So there the decision space was discrete. But in linear programming, the decision space will be like polytopes. They will be governed by finitely many linear inequalities. And your objective function will also be linear. So as you change the nature of your decision space and the nature of your objective function, in fact, it will spawn new fields of study. And that is because like abstractly we may have framed this, but the actually efficient solutions very much depend on the class of problems you're trying to solve. Okay, so let me give some general examples. So I wanted this part to be very, very clear. So for example, least squares problem. So this is a very standard problem in statistics. I mean, least squares is a very general problem. It comes up in signal processing. Since we have not done any Fourier analysis, I mean, if you had seen things like, for example, Parseval's inequality and so on, it would be very immediate, like what a least squares problem means. But at some point, I'll actually give you that example, like starting from first principles, because it's very instructive, like how to give a best estimate. In linear regression, what happens? If you have not done linear regression, let me just state the problem. In linear regression, you essentially have a bunch of like values here, x1, x2, xn, and you have observed some values of the corresponding yi's. So the model kind of looks like yi equals beta 0. This is beta 1 xi plus some epsilon I. So you want to say that this is essentially some perturbed term of a line. So you have a line, but what you're observing is not really a number, like it's not a function, but rather you're observing from a distribution. So epsilon I is something like normal 0, let's say, with constant variance sigma squared. So the real value is this, supposedly, for this function. But what you're observing is a perturbation of the real value. But what you want to do is, based on your observed value, you want to find the best fitted line. So purpose, best fitted line to the data. So data kind of looks like a blob and it has a trend. Perhaps you can look at the data and say, okay, there is a trend and I can just draw a line, but how do I find the best fitted line? So now you saw the word best, you immediately think, okay, best just means optimizing something. So I need an objective function. So what is my decision space here? Quick answers?
Like all possible lines.
Exactly. So there are two ways to look at it. In fact, after this, the alternate formulation, I will say this. So can you, whenever you answer, can you please tell your name also? Because this is the only way in this video medium to know people. So can you please, so who asked the question? Can you please introduce your name?
Yeah, my name is Srivatsa.
Srivatsa, okay. So yeah, Srivatsa said, correctly said that the decision space is the space of lines. Or in other words, you could just say beta 0, beta 1, if you want to talk about column vectors, take a transpose in R2. So this is supposed to be the intercept term, this is the slope term, and the decision space is this. In fact, this is an unconstrained optimization problem. There is no constraint really, it's all of R2. You are free to choose beta 0, beta 1. Sometimes you might just say, okay, I don't really want a line which is kind of the y-axis or something like that. But in this case, let's just say it is an unconstrained optimization problem. But you also need an objective function. We want to say best fitted line, but what does it mean to say best fitted? We need a cost function. So anytime we deviate too far away, like for example, if the data points are here and my line is here, I want to say this is not good. It's kind of far away. So typically in least square methods, what happens is the objective function looks something like this. So you want to say that yi, so let's say these are the observed things like I equals 1 through k or something like that. And essentially, there are many measures you can use. One of them is this. So g of beta 0, beta 1. So this is the objective function, or f0, since we are using that. Let's just stick with f0. I equals 1 through k. So you want to minimize f naught, because that will essentially give you like those values of beta 0, beta 1, where at almost every point this is close enough. Of course, you can always argue, why do I choose a square? Why not something like this? Absolute value of y. I mean, it's expressing this same general idea that you want those values of beta 0, beta 1, so that for any value of I, this thing is close to yi. So that would mean like it to be a good fit, or even the best fit if you're optimizing it. So yeah, you are in fact free to choose that, but here typically there is a good analytical solution. So there are many advantages, like theoretically you can study, like once you take statistical inference, perhaps you have seen some of it, perhaps not. Actually in the second year you have not seen linear regression in its entirety. But yeah, I mean, then you are able to estimate, like as a random variable, what are the values of yi, and whether it's an unbiased estimator, and those like theoretical things you can actually do for this least squares estimate. But anyway, just keep in mind that you're free to do this if your problem like demands that. And in fact, this problem can be analytically solved, but this actually is almost impossible to solve analytically. But you can immediately see that this starts looking like a linear programming problem. So here you may not have an analytic solution, but you can programmatically or algorithmically solve this. But any case, that's an aside. My whole point is that this is an objective function which we want to minimize, and we'll be doing that later in this course. But for now, this is just the framework. We want to minimize this. So if you have done some multivariate calculus, which is analysis 3, you'd recognize I will just take the gradient and equate to 0. Just like in one variable, you take derivative to find like local minima and those type of things. You take the derivative and you set it to 0, and you get some candidate choices. Then you evaluate the value and find global minima. So essentially in multivariable calculus, you'll be doing something similar. And here, this is a quadratic function. And note that in one variable, what happens to quadratics? They look something like this. Or if like the leading coefficient is negative, it will look something like this, like a parabola. And a parabola is convex. And so this should bring you this word, convex optimization. So although this least square problem is not linear programming, definitely the objective function is not like that. And there is no, I mean, since it's unconstrained, of course, the decision space is linear, but the objective function is not linear at all. But still, this has the very good properties of linear programming because this is a convex function. It's a quadratic function. So we'll come back to that later, but just something to keep in mind. Alternate formulation. And this is where I'm going to exactly phrase it as Srivatsa said. Here I was saying decision space is R2. Here I will not say decision space is R2. Of course, the answers I should get should be the same. Here I'll say decision space is space of all lines in R2. There is a difference. It's a subtle one. This is what is known as the affine Grassmannian. If you have come across this term, affine Grassmannian. So let me call it graph 2-1. 2 refers to R2. This is the space of one-dimensional things. So you can imagine, like in general, if you have heard these terms in data science and so on, you have some high dimensional data and you want to bring it to certain low dimensions so as to be able to visualize and study it. If you have heard these kind of buzzwords, this should bring into mind when I'm trying to project, what am I doing? I'm choosing subspace. It's best in certain ways. It is the best subspace in certain way, and I'm projecting to that. Whatever that certain way is determined by the cost function or objective function. So those details, maybe in due course, we will see that. But there, instead of graph 2-1, you will have like, you are looking at space of all k-dimensional subspaces in n-dimensional space, and we want to find the best one. And this will be a parameterization of this space. This beta 0, beta 1, in a sense, is a parameterization of this space using the slope and intercept. In general, it can get very complicated. So now you should be able to see why I was not starting with constant functions in the very beginning. I said just decision space and objective functions. Because as you go into optimization, if you phrase the problem the right way, you can actually work with very fancy and nice spaces, and arguing theoretically or arguing mathematically becomes much easier in that case. So here, anyway, yeah, so decision space is this, and objective function is f0 of whatever line you have. Anyway, we have parameters using beta 0, beta 1. We will use the same objective function, but it's just a slight change of point of view, which makes it very very useful actually. Okay, so that was example 1. That was about least squares. So decision space was unconstrained and the objective function was quadratic. The second example, example 2. So this is actually going to be like 50% of this course. A major chunk of this course is about linear programming. So here, typically the problem will look like minimize something like C transpose X. Perhaps I'll okay, let me put a bar because it otherwise, so it's a vector, it's a column vector. In fact, Cx will be column vectors. Yeah, minimize this subject to. So essentially, it's if x1, x2, xn are the decision variables or the optimization variables, so your objective function is linear in those variables, and the constraints are also something similar. So ai vec transpose x vec is less than equal to bi. So bi is in fact just a real number. So I equals 1 through n. So here, the vectors C, A1, AM, they are all in Rn, and B1 through Bm are all in R. So these are the problem parameters. So these are the problem parameters that specify the objective and constant function. And constant functions. Okay. So yeah, as I said, this will be the main chunk of the course. And we'll do that, but let's see a couple more examples. So example 3. And like I said, as you change your decision space and your objective function, it actually is not a trivial change because it actually spawns new fields of study. And in fact, example 4, once I give it, will look very familiar to you from your physics 1 course, from your classical mechanics course. That is just to pique your interest. So right now, let me finish my example 3 first. So that is about optimal transport. So what is optimal transport? This is actually, in fact, an old problem from the late 18th century, kind of studied by the French engineer mathematician Mons. So it was formulated by Monge in 1781. So what's that? The most basic thing is like you have some mines, let's call them M, and you have some factories, F. So there are some locations assigned to that, and you want to move, you want to transport. You want to transport things from the mines to the factory. In fact, it is framed this way, but you can think of it in different ways also. Like you are building a house and you have certain, you're digging things here and you're making materials. Maybe you're making compressed earth bricks. So there also, it doesn't have to be just mines and factories. You can imagine whatever you're transporting, there is a cost to that. Perhaps there is like a low density of ore or something like that. So perhaps it is not worth it, or maybe geography is not good enough that you have to travel a lot more. You have to wind around hills in very like serpentine paths and get to your factory. So those kind of things might be there. So this is the transport problem. So cost function, what is the cost function? So let's call this space X, this Y. So points, these are just points. So it's actually much easier to describe. So there is a cost function from here to R plus. And what does the cost function do? So it's the cost of transporting a 1 kilogram of ore from X to the factory Y. Cost of transporting, say, ore from point X or mine X to factory Y. And you want to optimize your cost, overall cost. So then, what is a transport plan? So transport plan is essentially a map. It's a map T from M to F. Right, mines to, okay, perhaps I used X and Y. Instead of that, maybe I should have used M and F, since I have done that already. So let me just stick with X and Y. So transport plan is a mapping from X to Y. So it is assigning to every mine a factory. So this mine, whatever you're getting, you should send to that factory. That's what it's doing. Now the optimal transport plan. So for that, so we want to find the best transport plan, which will cost the least. optimal transport plan. For that, we have a decision space that is f to the m. This is or x to the y rather. This is just set theoretic notation. Set of functions from y. Okay, it should be y to x. The decision space is y to x. What is this? Set of functions from x to y. From x to y. And what is your objective function? It is C of t, where t is a transport plan. So t is an element of this. So C of t is, what is the definition? It is summation. If there are n points, so it is C of x tx. So you're sending x to tx, and let's say x belongs to capital X. So this is by definition your like cost function. So for your transport plan. So again, like here, look here, decision space is not something very traditional, not about constraint functions and so on. I mean, if you are like imaginative enough, perhaps you could do that. You can represent it in this form, but you can see here that decision space can be very exotic. Here it is a set of functions from x to y, and the objective function is in fact a function on the space of functions in a sense. So this was example 3, and this is in fact has become very useful, especially in physics in recent years. In fact, 2010, like a Fields Medal to Cedric Villani, and 2018 to Alessio Figali was for work in this area, optimal transport. It had a resurgence in the past 30 years, you could say. For a long time, it was lying dormant. Because it could give very nice solutions to many geometric problems, like in differential geometry, and also in the 40s and all, it was developed mostly for applications to economics, like I think it's known as Monge-Kantorovich formulation. But yeah, in recent years, it has become very applicable to mathematical physics. All right, so this is again another optimization problem. But of course, like I said, as your decision space changes and the nature of your cost function changes, the methods you'll be using will also change. The key focus of this course will be example 2, linear programming, and also a little bit example 1. But this is something to keep in mind when we are talking about optimization. Like a lot of mathematics is all about finding the best this, finding the shortest this, and like geodesics are the shortest curves from this point to that point. So a lot of mathematics is about optimizing. So it's good to like phrase it in your mind in this sense. Now we come to example 4, and this is from physics. Variational analysis. Perhaps you have heard of the term known as least action principle. Like, I mean, you have Newton's laws of motions for physics, but there are many other formulations. There is the like Lagrange formulation, there is the Hamiltonian formulation, and they're all equivalent. Mathematically, they're all equivalent, but depending on which problem you're looking at, what type of symmetry it has, some of them are more interpretable. So mathematics, you should not think of as just theorems and proofs, and like that's not true at all. Perhaps in the book it is presented that way, but that is not true at all. And giving different proofs kind of gives you different points of view of how to like think about it, and and give a like interpretable kind of idea, so that you can go even further, like beyond what you have done. Yeah. So variational analysis was somewhat about least action principle, meaning there is you have a configuration, you want to move from this configuration to the other. Like for example, if some heavenly body is orbiting another heavenly body, so the configuration is changing every moment based on Newton's laws. And from all possible things, the least action principle will say something like there is something called an action for each path in the phase space, and you want to minimize that. Yeah, I mean, enough in abstractions, but let me give you a concrete example, the brachistochrone problem. Perhaps maybe Dr. Sinha taught you physics 1, or maybe Dr. Paul Chattopadhyay. But towards the end of the course, there is a little bit about the Lagrange formulation of classical mechanics, and you may have seen this, the brachistochrone problem, which essentially says you have A and B, say B is lower than A. B is lower than A, and you want to draw some sort of curve so that anytime there is a frictionless kind of path, let's say, and you want to find the curve of fastest descent. So question, is what is the curve joining A and B of fastest descent. Of course, there are some assumptions. So there is a bead here. This is the typical formulation of the Brachistochrone problem. So bead slides frictionlessly under the influence of a uniform gravitational field. So that's the assumption. Of a uniform gravitational field. Okay. And this was posed by Johann Bernoulli, 1696. And many solutions are given. One of them was also due to Newton. And so here, how do we think of this problem? What is the decision space? Here, the decision space is a space of certain like nice smooth curves. So you have A and B. So it's all these type of curves. So I'll put curves in like quotes because I'm not specifying what type of curves. Like, is it smooth or piecewise smooth? So I mean, take your best pick. So perhaps for simplicity, you can just take all smooth curves, meaning it is differentiable everywhere and there are no sharp edges and all these things. So curves joining A to B. So that is a decision space. You have to choose, like you want to find the space and what is the objective function here? Can anyone just prompt? What is the objective function here?
The distance along the curve from A to B.
Not quite. It's the time taken to travel from A to B.
Oh.
Yeah. So time taken to travel from A to B on that curve. So it will be a function of that curve, right? So time taken to travel from A to B. So you think of this as a function of the curve gamma. So this is the objective function and this is what we minimize. So again, this is again an optimization problem, but your space has changed. So that has given rise to what is known as variational calculus. So you can think that as you change your space, like this kind of spawns new fields of study. This is not easy. It's not like, essentially many fields of mathematics, especially the hard analysis, are like that, like partial differential equations. There are some basic ones like heat equation, wave equation, and I forget the usual third, but yeah, I mean, there are some standard equations that people know how to solve. But in any new PD, there are no standard techniques. If you have homogeneous PDs, I mean, of course, this is nothing related to this content of this course. I'm just drawing an analogy. So if you look at more abstract fields of study in mathematics, there is generally a very clear structure, like very clear first principles from where you should start, and everything else will follow from that. But in many fields in hard analysis, that turns out to be pretty much not what it is. Like PD, any given PD forms an industry of its own because it needs its own techniques and own strategies and so on. And combinatorics a lot of the times is like that. And not to say that every 50 years there are some unifying principles found, just like Giancarlo Rota for combinatorics, he did so in the 60s and 70s. And in fact, like he gave some of the very fundamental like what are the like fundamental techniques for counting and so on. But this is something general you should see. Here also you're seeing an example. I could phrase optimization as a general problem, but as I'm changing my decision space and objective function, I need techniques which are specific to that. Okay. All right, and this will be the last general example, again coming under this variational analysis. So isoperimetric problem. So isoperimetric problem is what? It's here the decision space is the space of closed plane, or I'll just tell you what this means, rectifiable curves of a given length, L. Let's say the length is L. And objective function is area enclosed by the curve. maybe I can add another assumption like simple or something like that. But just think of it that way, like it is a curve with a given circumference and it is not self-intersecting, let's just say that. And rectifiable just means that it has a length. Because if you have some acquaintance with fractals and these kind of things, you can have like a curve which is in a compact domain, but it has infinite length. And a very standard example, yeah, you may know that. So you draw an equilateral triangle, then draw something like this on 1/3 and keep doing that. And it's very easy to compute that whatever the limiting curve will be, it's a closed curve and it's a simple curve, but it has no length, no finite length. And it will enclose finite area, but does not have finite length. So for those technical reasons, I'm just saying rectifiable, meaning it has finite length, so that I can even talk about of a given length. So isoperimetric problem is essentially finding that curve of a given length so that it encloses maximum area. So you want to maximize this, maximize objective function. So for example, minimization problem is not very interesting here because I can always choose a very thin strip. The circumference might be L. Let's say this is like L/2 plus minus epsilon or something. This is epsilon, and this is L/2. The circumference of this curve is L, but the area enclosed will be very small. It is like epsilon times L/2 minus epsilon. And as you can see, as epsilon tends to 0, this will go to 0. So the minimum problem is not very interesting in this case. What is interesting is the maximizing curve. And that turns out to be a circle. So the maximal area will be, in fact, so circle of radius r. The answer is the circle of radius r. So maximizing area will be pi r squared, so something like this. Anyway, so this is again a question of variational analysis. So I hope you got a general idea of how to set up an optimization problem. So here are a few comments about solving. So this lecture, actually, today's lecture will mostly be about setting up the the general theme of the course, like what problems we think are important, what problems are, at the end of the course, we should look back and say, okay, these are the problems we wanted to do. And I have a general idea, not just I can solve it mathematically, theoretically. I also know how to write it in a computer and do it in an efficient manner, effective manner. The word I would use is effective, meaning it wouldn't take 100 days to run, for example. If it does, then it is not effective. It should run with like given memory and given time and so on. So all these aspects we should try to cover. Okay. So now let's talk about solutions, like generic comments about solutions. So we generally consider families. Consider, let's say, families or classes. Families or classes of optimization problems. And these are characterized by the, this is just a repetition of the comment I made like a few minutes ago. So the family, linear programming is a family, variational calculus is a family. So these are like families of optimization problems. And for each family, we will have certain nice algorithms, if not like analytic forms. Okay. So characterized by particular forms of the objective and constant functions. Okay. So here a remark is the algorithmic and numerical aspects will change based on the family that you choose. Change based on the class of problems or family of problems. And just capture all this in a very pithy kind of phrase: devil is in the details. And we want to find the devil. Okay, so the optimization problem is called a linear program. So it's called a linear program. If both objective and constant functions are linear. So that's a family. They're characterized by linearity. If both objective and constant functions are linear. And I mean, you know the definition of linear, so but I'll just write it out. That is, they satisfy fi of alpha x plus beta y is equal to alpha times fi x plus beta times fi of y for all xy in the decision space. For all xy in Rn, let's say. Okay. Yeah, and you might wonder, like, do we really want linear or do we want affine linear? There's a difference, right? When I say linear subspace, I mean the origin has to be in there. So perhaps I should call it affine linear program, but it's just a cosmetic difference, you could say. And the reason being, you know, like you have an objective function f0x. I mean, if I can minimize f0, I can always minimize any translate of f0. So no worries there. So this being affine linear, like, doesn't change things. You can always linearize it. And if I have a constraint like fix is less than or equal to bi, and let's say this is affine linear, whatever is the translation part, I just move it to this bi. So in that respect, although I'm calling it linear program and all these functions are linear, it is exactly equivalent to saying it is affine linear. Yeah. So that would be just like a change of coordinates, like a translation. Okay. So here, the decision space is a convex polyhedron. Actually, this word polyhedron is so overused, it's never even clear what is it exactly means. But what we will mean is a connected, some possibly unbounded. For example, half spaces for us will be polyhedron. Half spaces meaning, let's say I have this, and I'm looking at the upper half plane. Then this is, for us, it will be a convex polyhedron, and so on. And this is precisely given by y bigger than or equal to 0. This is the constant, right? If I'm talking about coordinates, let's say x2 bigger than or equal to 0, x1, x2, then x2 bigger than or equal to 0 is exactly this space. And since fi's are linear functions, essentially something less than or equal to bi. We'll do it in details in the next lecture on Thursday, most likely, when we talk about convex sets and how convex sets are determined by supporting hyperplanes and so on. So here you can imagine fix is equal to bi is like a affine hyperplane, right? And something less than will be on one side, something bigger than will be on the other side. So the set of all these constraints will be intersection of these things. So essentially it will be looking something like this, ignoring these parts. So the intersection of all these half spaces will result in a convex polyhedron. So the decision space will look something like a convex polyhedron, and the function you want to optimize will be linear. So typically you can very easily argue that the whatever maximum minimum will be attained will be at the boundary. I mean boundary or at infinity, if we want to call that the boundary also. In any case, so you have the decision space and your objective function. Oh yeah, I should say convex polyhedron with finitely many vertices. Finitely many vertices, because I have finitely many of these. For example, some literature would also call the solid ball, like let's say it's the all the vectors whose length is less than or equal to 1, like centered at the origin. So this is also a convex set. Some literature would say that this is also convex polyhedron, and this is determined by infinitely many such hyperplanes. Here we care about finitely many. So that's the difference. That's why I should say the decision space is convex polyhedron, which are generated by finitely many vertices. Okay, and the objective function is some linear function. So linear in x1, x2. All right, so that is linear problem. Now, the more general class is what is a convex optimization problem. So here, both the objective and constant functions are convex. So just like we said, so in this case, we said it's called an optimization problem is called linear program if both objective and constant functions are linear. And a convex optimization problem is one where both are convex. So here, objective and constant functions are convex. That is, you have fi alpha x plus beta y is less than equal to alpha times fi x plus beta times fi y for alpha beta in R such that alpha plus beta equals 1 and alpha bigger than equal to 0, beta bigger than equal to 0. So yeah, I mean, alpha x plus beta y is a convex combination. So if I evaluated on that is less than equal to convex combination of fi x, fi y. So these objective and constant functions are convex. And immediately you can see this inequality I can always replace by an equality, and by appropriate scaling, this like saying that alpha beta is 1 is not necessary if I assume fi is linear. So any linear program is in fact a convex optimization problem. Any linear program is a convex optimization problem. Okay. It's just a matter of replacing this inequality by an equality. So it's contained in here. And the good thing about convex functions, if you even think in just one dimension, the example I gave was of the quadratic, which is like a parabola, is typically when they have a minimum, it is unique. I mean, especially if it is in the interior. On the boundary, you'll have to check. So for just like in linear, in the linear program, whenever you're trying to optimize, all you have to do is look at the boundary. Here, of course, I'm not claiming that, but what I'm saying is you have to look at the boundary plus some few finitely many points. So that's the good thing about convex optimization. And another thing, thing is that if you try to flow along these functions, typically you try to flow towards that unique minimum or unique maximum. Like if you have all these gradient descent methods and so on, which we will cover later once you have learned about all these partial derivatives and gradients in analysis 3. So I think I should push it until like middle of the course, talking about gradient descent and so on. But it is just a matter of implementing Taylor expansion. Like Taylor expansion is what? F of x, f of 0 plus f prime 0 times x plus you have some order x squared term somewhere. Or a little o of x term, in fact. So this is essentially, if you're trying to even solve equations, polynomial equations, there is a method known as Newton's method. So you try to move along the direction where it is decreasing. If f prime is negative, you move along, and ultimately you hope that you will hit a minimum. At some point, you'll have to like go down and down and down and hit the minimum. So you do it iteratively. That's the general idea. And in higher dimensions, this is what is known as like some sort of gradient descent. So with convex functions, the minima will be unique, or the maxima if either exist. For example, maxima here will not exist in the interior. So yeah, so that's what makes convex bodies so nice. And the point made in the book is that convex optimization problems are not much harder than linear programming problems. So why not just go that extra mile and learn to solve a large class of problems other than just restricting to linear programming problems. So yeah. Okay, so now let's come to some real world examples. So previously we saw general examples, mostly like mathematical examples. So let's see where this can be applied in the real world. Example 1. So portfolio optimization. A very standard thing. I guess you guys are too young, or maybe you have some experience. Like MFs, you may have heard mutual fund. Lot of ads in TV come up these days. Mutual funds, ETFs, and so on. Essentially, what do these mutual funds do? So you have certain asset classes. So you want to the term you'll be hearing, the catchphrase you'll hear is diversification, right? Like, or they'll say, okay, don't put all your eggs in one basket, blah blah blah. They'll say a few things like that. So the whole idea is that you want to manage your risk. You want to get high returns, like based on your investment. You want to get high returns, but at the same time, you want to manage your risk. Like perhaps you're feeling risky in the sense like you want to take a gamble, like be a punter. So in that case, you want to go for something which will grow rapidly. At the same time, it might even go to nothing. So mutual funds, essentially what they do is assign certain risk and reward to each asset class. Asset classes could be as specific as a single stock, could be Google, Apple, whatever, or it could be as general as like rare earth metals, insurance, or like soybean, like animal feed. It could be that general. So you have all these asset classes, and you have some traditional returns for this. So based on historical data. So based on historical data, we have an idea of two things. There are two things involved. Idea of so I want to say expected return. So I'm writing that in green. And risk. Of course, like these are generic terms. When you want to do mathematics, you want to say what exactly they mean. So risk is variance. So in the historically, like if something is fluctuating like this, it has high variance. So perhaps you bought here and the price goes here, or you could get lucky. You could start here and get here. So that's the risk historically. And expected return is the overall trend, general trend. So an optimization problem there might look like something. Oh yeah, by the way, and you have a fixed amount of money. So you start, that is a constraint again. So think of that as a constraint. So you start with, let's say, 10,000 rupees. So this is your like investment. So like whichever way I split it up into these different asset classes, the sum has to be 10,000. So that's already a constraint. And the objective function is to maximize this expected return. But at the same time, you want to control your risk. You want to maybe not minimize. You don't want to minimize risk. Then what? If you want to minimize risk, you can always set risk to zero. How? You do an FD, you do a fixed deposit, or you buy a government treasury bond. Like different governments, like the US government or many countries in Europe or China or Japan or even India, they have treasury bonds, which will give you low returns, but they're guaranteed. So if you say that, okay, and if you go to a portfolio manager and say, I want completely zero risk, then they'll give you that standard return. So that's why you definitely don't want to say that I want zero risk. What you want to say is I want to manage my risk. I want to set an upper bound on that risk. So perhaps you'll have W1 plus WN. So maybe N asset classes are there, is 10,000. And then you have expected return, W1 R1. So maximize this. Constraint is W1 squared or sigma 1. Let's say the variance for each of these asset classes, something like that. And you want to set it, let's say something like, just put a number 100 or whatever. So this is again an optimization problem. And this is also in economics, and all this is a big subject in itself, portfolio theory, as I said. So this is also a very useful optimization problem, which people use in their daily lives on a day-to-day basis. Okay. Example 2 is also quite relevant, especially in today's world. So that's why I wanted to bring this up. What is known as supervised learning. So like machine learning, all these kind of things you see. Whenever you're talking about machine learning, of course, that's like a fancy buzzword for neural networks. So neural networks is like you have these nodes and you have these like transition probabilities. and you have some input, and you want to make a decision at the end. So decision could be, it could be classification. For example, it could be classification. Is this, in this image, is there a dog or a cat? Is this a table or a chair? So that is image recognition. I mean, machine learning is a broad term, but you can think there are specific problems like digit recognition. You like handwritten digit recognition. Like for the postal industry, that is useful. They just want to scan it instead of someone having to read it. In a very scalable manner, you can scan many letters and see, okay, what is the address written on the top? So handwritten digits. Or like OCR software. Again, OCR is, you look at a scanned copy and you make it into digital text. So optical character reader or character recognition tool, OCR tools. Or you can think of other examples like self-driving cars. At every moment, they have to make a decision. Does this look like a human? Should I stop right now? Or does it look like a polythene bag just floating around? So all these decisions have to be made. And remember, what was the thematic question? It was, we want to make the best decision towards a particular objective. So this question can become very complicated. Like you have that trolley problem, right? For a self-driving car, it can be, should I choose, like, let's say there is an accident situation. So trolley problem is the following. You have a trolley and you have rail tracks and a rail track here. And you are going along this normal track. Okay, perhaps I should draw the rail track here. You are going along this normal track and there are 5 people tied here on the rail track. So if you just keep going, you'll kill all those 5 people. The other thing is you can make a decision. You can actually pull a lever so that you actually change your track, but there is one person here. So, I mean, immediately one would say, okay, I mean, of course, one person dying is probably preferable to 5 people dying. But the thing is, here you have made a decision to, here this guy was safe. He had no idea that this was coming. These guys had that idea. And you have made a conscious decision to actually go and like hit this guy. So this is a question in ethics, right? So if you Google around the trolley problem, you'll come across this. So a self-driving car always has to, I mean, this is of course a toy problem, as they say, or a thought experiment, but a car always has to make that decision, right? I see something, I want to stop, but I cannot stop. So should I swerve? Should I go do this, do that? So all these type of ethical decisions, all of this has to be made. So decisions have to be made based on various constraints, or it could be as simple, not as complicated as this, but it could be as simple as, okay, like I want to save on fuel. So what should be my fuel injection mechanism be like, based on, like perhaps I'm in a high altitude where there is less oxygen available and blah, blah, blah. So you want to design your control system that way. So all of these, you want to do it real time. So the point is you want to do real time optimization. So essentially your parameters are changing and you want to optimize based on that. Yeah, so that is one type of problem. But in supervised learning, what happens? So typically, just to give you an idea what happens, you have some training data and you have this neural network and you want to figure out what these parameters are, like P, I, J, where I is the node here, J is this node here. You have some probabilities of moving around here. And at the end, you get a score, let's say between 0 and 1. If it is close to 1, yes, it is a cat. If it is close to 0, no, it is not a cat. Or you can have different classifications like that. So in the training data, what you do is essentially you have labels, like you have pictures of cats or dogs, whatever, or furniture. So you have picture like C1, C2, C1000, and you have kind of drawn and you have labeled them. Okay, all these pictures have cats in them. And based on that, it will learn all these parameters. Based on that, this very complicated neural network. If it is deep learning is just a fancy word of saying I have many nodes. I have very deep, like a lot of nodes in here. Of course, the details, if you are not aware, it's fine. I'm just trying to give you an overview of what happens. So you want to train these parameters, and based on some cost function. And how does that cost function derived? It is based on this training data. So training data, you have like you know that C1 should be 0, C2 is 1. Like for example, you have some pictures where there are no cats, where there are some cats. So you know what the answers are. Exactly like the linear regression problem. You have xi, yi. You're trying to give the best fit. So here, similarly, you want to give this best transition probabilities, which will match with the training data. And then you'll use it on the untrained data. So this is called supervised learning because you have this training or supervision data. And once you have trained these parameters, you want to use this model, you want to put an arbitrary input, and then it will give you a number between 0 and 1, like based on these trained parameters. And you'll say, okay, if it is close to 1, I'll say, okay, it's a cat, there's a cat. If it is close to 0, I'll say there's no cat. So how does this relate to optimization? Like in the training process, you're trying to find the best parameters which are fitting to the labels, like what you already know. So to what you already have collected data from. So here also, optimization problems show up. Okay. So we have seen some general like mathematical physics examples and more like down to earth and let's say real life examples. Okay. So our next goal, like now that I hope that we have been convinced that studying this subject is worthwhile for more reasons than one. So we'll move around to getting into the details. So solving optimization problems. All right. So just like we talked about families or classes of optimization problems, and we also mentioned that each class will have its own like idiosyncratic solution strategy. So that's what I'm describing here, a solution method for a class of optimization problems. Is an algorithm that computes a solution of the problem and of course, like unless it is some closed form mathematical expression, you don't expect that when you say solution of the problem, we can always find an exact solution, but to some given accuracy. And given a particular problem of that class. I mean, that's what algorithms do, right? They don't give you a closed form solution in general. They don't give you an abstract solution. They tell you that if you give me the particular instance of the problem, if you give me like the sorting algorithm I mentioned, it doesn't say I'll give you a general formula given A1, A2, AN. What it does say is if you give me numbers A1, like 1, 2, 3, or like 90 or some, you give me 100 numbers, I can always do it. So that's a particular instance of the problem. So given a particular problem from the class. So in the sorting problem, the class is just a set of 100, like vectors in R to the 100. So which is also known as an instance of the problem. Yeah, so solution method is typically an algorithm which will solve your problem. I mean, it's as simple as that, but very important to keep in mind that closed form analytical solutions are very rare. Are rare. I don't say impossible, I say rare because, for example, example one we saw was least squares, right? There we can actually find an analytical solution, although that analytical solution itself will bring some numerical issues with it. When we study that, we'll see that. But typically closed form analytical solutions are rare. And if you're not familiar with this term, it is like, you know, when you solve the quadratic, you have a closed form solution. If I'm trying to solve x squared plus bx plus c, I know that x must be minus b plus or minus b squared minus 4 is 4c divided by divided by 2. And for cubic, you have certain solutions. For the quartic, you have, but for the quintic, you don't have general closed form solution. In particular instances, you may have some solution involving radicals and all those. But as a general principle, you cannot have that. That is the discovery of Abel and Galois independently. Perhaps you may have seen it, or you will see it in your field and Galois theory class. But just to draw an analogy, so or you can even talk about like integral of e to the x squared, for example. There's no closed form. Closed form meaning involving elementary functions like exponential, trigonometric functions and polynomials and so on. So that's the way I mean. So closed form analytical solutions are rare. What we want are effective methods. So I want to stress on that word. Anytime you do some applied mathematics, that is what we want. Things that will work in practice. So effective methods or solutions to our problem. So effective means it should run within a stipulated time, and depends on how frequently we want to use it. So if this is something which is real time, of course, we want to do it in seconds rather than minutes. And if it is something which we do once a year, okay, we'll be fine with that algorithm running for 7 days. And that is not an exaggeration. Many of the algorithms in real life actually can run for days or even months. But if you can afford that, that's it. So effective, of course, depends on, what context you are in. All right. And another remark. So we don't just care about a mathematically provable algorithm. So we don't just, we do want a mathematically provable algorithm, because otherwise we wouldn't even know that this algorithm solves our problem. And if this sounds a bit surprising, that how can you have an algorithm which is not mathematically provable? In quite applied areas, people actually look at the data and go by their hunch and build algorithms and test. And typically, you may not even have for a long time any mathematical proof of those algorithms. And you could say that that is a travesty. You could say, but sometimes actually it's a very interesting phenomenon. Okay, let me finish this thought and then I'll give you an example of that also. So we don't just want a mathematically provable algorithm to find a solution. We also want it to be efficiently implementable. On a computer. It's essentially a rehash of what I said. What we want are effective methods. It's just a restatement of that. Ideally, whatever algorithm you have should be mathematically provable. In fact, that is like a good quality algorithm. But sometimes you just want to get the job done. And if you notice like somehow that you just cooked up some random algorithm in your head, you thought that, okay, it looks plausible and it works out. And it works out for many of your training data sets that you have, then you might feel encouraged to keep using that algorithm, although with a pinch of salt. And there was such an algorithm, I think in the 70s, to study like seismic waves and all those. There are some reconstruction algorithms. The details, maybe I'll share later, but they used, typically the methods used were L2 methods, least square methods, just like linear regression. But since least square methods didn't give very good data, they just pretended that they were doing something known as L0 method, L1, L2. So think of this as least square method. L1 is you're optimizing this type of thing. And this is L0 just means that you are not optimizing this. You're just talking about sparsity in your data, meaning you're assuming that your matrices are sparse. Most of your matrix is empty. You're making certain assumption like that. And then you're trying to solve like based on some rank conditions. So it turned out empirically, they said, okay, this L0 formulation can be equivalent to the L1 formulation. So we'll just use it using LP, linear programming, and we'll solve it. And it turned out to be much, much better than L2 in practice. And there was no proof of it until 30 years later. I think 2005 or 6, there is a field of signal processing known as compressed sensing. And the foundational theory was given by Terence Tao and he's a very well-known mathematician, so you may have heard of him, and Emmanuel Candice. So in that sense, I would say sometimes empirically people discover some algorithms that they work, but they have absolutely no idea why they work. But later on, like people with firmer mathematical background, and perhaps they see like why exactly it is working. So one should not denounce empirical stuff, but it is always better to have a mathematically provable algorithm. Okay, yeah, so that's just to give you a general picture. So if you want to look at this more, you can Google around. So the keyword I have given you is compressed sensing. But at some point when we're talking about topics, just as a fun like conversation during our lectures, I may explicitly state this problem. And although we will not be proving any results because it involves much more advanced tools, but I'll state some of the theorems and what they look like. All right. So the third remark I want to make is about real-time optimization. So I already gave the example that like perhaps like you have all these control systems in your vehicles, in your motorcycle or your car, whatever, like how to efficiently have the full injection system to increase your mileage and all that. So these days they have something known as embedded optimization. And of course, embedded optimization has been there around for quite some time, because if you send a mission to the moon, or let's say to Mars, it takes moon, at least it takes, I forget how much time, 2 seconds or something like that, 1.2 seconds. Or Mars is like 7 or 8 minutes, right? So you cannot expect that you will send a signal to your rover and they will like take the good decision, optimal decisions. In fact, you can show that if you don't want your rover to like strike a boulder or something, your speed of your rover can be like 5 or 10 kilometers per hour. It's because 8 minutes to send you a signal and you to send a signal. And so there is a reaction time there. So if it's traveling very fast and it sees something 100 meters ahead, let's say that's the visual it has, then it should not have traveled those 100 meters in those 8 minutes. So it can travel only really, really slow. So in some cases, you don't have an option, but typically you want some real-time optimization. Whatever device you have, it should act on its own, and whatever parameters it wants to optimize, it should do it on its own and in real time. So examples, autopilot in planes or minimizing fuel costs. So for that, other things also come into picture. So this requires solution methods or algorithms that are extremely reliable. And solve problems in a predictable manner, and solve problems in a predictable amount of time and memory. Time and memory. So yeah, so let's look at this a little bit, because whatever like embedded device you have, it has a cap, upper cap on how much memory it has, and what is the reaction time that you have. So an auto, you know, these days some motorcycles and all, they have ABS, automated braking system. So it has to take some input and it has very limited time to react. It cannot just say, okay, after 5 minutes, I'll think what to do. That cannot happen. So you have a hard upper cap on time and memory, of course, whatever is there in your device. So algorithms for real-time optimization need to have those hard upper caps. And also they have to be extremely reliable and predictable, in the sense, if your initial parameters, you have some errors, then the numerical error should not propagate. Like, or slight perturbations should not lead to like very varying like solutions, or there should be some sort of continuity. Like if you perturb your initial conditions in a continuous manner or in a smooth manner, then your output should also vary in a continuous or smooth manner. So all those are needed for real-time optimization. So that will also spawn its own fields of study and even more specialization, I should say. Okay. So for a few problem classes, we have efficient algorithms that can reliably solve even large problems. So large meaning large number of input parameters, decision variables, and so on, or number of constraints. We have efficient algorithms that can reliably be solved for even large problems. Okay, and here I'll just parenthetical remark effective methods. So I want to remind you, these are effective methods. So what are those problems? We already talked about a little bit. Least squares problem. Linear programming. And 3 is convex optimization. In fact, it's actually, it supersedes these two studies. But that does not mean we'll start with the like highest levels of abstraction and then specialize here. In fact, we'll go the opposite direction. We'll look at these very special examples. In fact, linear programming, the algorithm we'll study is known as the simplex method, due to Danzig, George Danzig, 1947. And once we learn some results like the general theory of convex optimization, we'll also use interior point methods, what are known as interior point methods. And I mean, it's not good to leave you hanging and just say some words. So here you can imagine like you have a convex body and you have a linear function and you're trying to optimize. You already know that it has to be on the boundary, because otherwise you have some direction of increase. It's a linear function. Either it's like a constant flat function throughout, or there must be some direction of increase unless it's on the boundary. So on the boundary, the simplex method is essentially an algorithm to find like the best vertex. So in fact, the best solution will be one of the vertices. I mean, or it could be multiple vertices, yeah, so it's a matter of finding which vertex gives you the optimal solution. So it's all about the boundary. So interior point methods, what they will do is in fact perturb the problem. So you have a linear problem, it will convert it into a slightly nonlinear problem. And then instead of shuffling around, like in the simplex method, you move around, you improve your vertices, you move around vertices, you do not care about the interior at all, in a sense. Interior point methods will tend to the solution from the inside, from the inside of that simplex and so on. So that is the main difference. And simplex method works very well in practice. The only issue is that in the worst case, what happens, does not have like polynomial time. It's not a polynomial time algorithm in the number of, let's say, vertices, number of pivots. So in the worst case, this can actually fail. But interior point methods, they will approximately give you the solution, but effectively almost in every case, it will give you the right solution. And you should note that here we had this quadratic objective function. Here we had a linear. Both of them are convex functions. So these are all subsumed by convex optimization. So that's why we want to keep this higher level of generality for the later part of the course. But initially we look at these two specific problems. Okay. And I'll just quote something. Actually, so this took me shorter than expected. So then we'll meet and start with concrete problems. I think this is a good point to end, like with a brief summary of what we have done so far. But I'll end with a remark which I saw in the book, which is very illuminating. So in fact, the great watershed in optimization is not between linearity and non-linearity, but between convexity and non-convexity. So the great watershed in optimization is not between linearity and non-linearity, but convexity and non-convexity. And I think I had roughly mentioned to you that the thing with convex thing is that the maxima is either attained at the boundary or any kind of optima, maxima or minima. They will be either attained at the boundary. If at all within the boundary, there won't be there too many, like maximum one, like you will have maximum one or something. So it's not that different from linear programming. And the whole point of the textbook is that you can effectively use similar methods to solve both problems, or you can generalize LP to convex optimization problems. All right. So I guess I'll end the lecture here. And if you have any questions, please feel free to ask. So next time we'll start with some basic concepts in convexity. So let me just kind of give you a heads up about next class. It will be about very general concepts. So now that we have understood that, to even frame our problem, we need to understand about convex bodies, and we need to at least recall some basic linear algebra. So it will be review of convexity, linear algebra, and so on. So essentially, chapter 2 of the book on convex optimization, and also some general linear algebra concepts. Okay, so we'll start up with the hard math in next class. So I'll be here for the next 5-10 minutes. If you have any questions, feel free to ask or write it in the chat box. And also please introduce yourself and then ask the question. That way we all get to know each other. Yeah, any questions?
Sir, sir, I am Sahib. I have a question regarding the alternative formulation. Could you repeat that?
Yeah,
could
sure.
you repeat what you said?
Yeah, let me. Yeah. So you're talking about the linear regression thing, right? The alternative formulation.
Yes.
Yeah. So there. So in linear regression, we wanted to maximize this objective function, beta 0, beta 1. Yeah. So here the decision space, I said, so we are trying to find the best fitting line. So the decision space, I said, you can think of as the space of all lines. Okay. So the alternative formulation, the difference is subtle. So it will be clearer when we go to higher dimensions. Here it's because I'm parameterizing every line by this slope and intercept. So it almost looks like, okay, this is isomorphic to R2 in the appropriate sense. So then why make the fuss? But what I'm saying is, when you think about it, let's say I have this high dimensional problem, so R to the 1,000 or 10,000. I have some, typically, let's say I have some genetic data. So let me give a concrete example. So there is one person. So humans typically will have 20, 30,000 genes. So for each of them, you have some expression level for the gene. So what you have is a vector, which is around 20, 30,000. It's a very high dimensional vector. But once you have done certain treatment, let's say you have given some drugs, some gene therapy or something like that, and you want to figure out what genes have been affected. So and how they have been affected. So most of the genes will not be affected. So you want to kind of reduce it into very a low dimensional space, and perhaps it's not just genes. You may also care about like gene families, perhaps just formally think of as linear combinations of genes. So then I want to reduce this into, let's say, 100-dimensional space. So dimension reduction. So 100-dimensional space. So dimension reduction, like from 10,000 to 100. So what this means is I want to choose the best 100-dimensional space in the 10,000 dimensional space based on some parameter, right? Perhaps it is the best fit, or maybe it has the least variability. Like, for example, if in 2 dimensions I have a data set which looks like this, then I clearly know that this variability is very low. So this could be just because of noise. So in fact, my data should look like this. And in higher dimensions, something similar could happen. Like if variability in a certain direction is very low, you want to say that actually it is just due to some noise. So in fact, your data lives on a lower dimensional space. It's just that due to noise, it looks like it lives in a higher dimensional space. But in order to find that, you may want to optimize. You may want to say, okay, I want to look at this variability. So I have this blob of data points. So in each given direction, I will, let's say I will measure the width. So I get a function v on Sn-1, which is the sphere of n-1 dimension. Then it gives you a number. It gives me the width. And I want to minimize this. I want to find the direction where there is minimum width, and then they'll ignore that direction. I'll just take the orthogonal complement of that, and I'll keep repeating that process. So here, actually, since I'm dealing with 1 dimension, it's very easy to visualize. But let's say I want to talk about multiple dimensions simultaneously. It's not just the width I care about. Perhaps I have some other measure where I have something like a cross-sectional area. Like I look at all hyperplanes, and wherever the cross-sectional area is minimum, this is the space I want to choose. Or maybe it is maximum, wherever the hyperplane cross-section is maximum. So then what is your space? So it's the space of planes, right? So now V is a map from what to what? From space of planes to R. So now this is what is known as the affine Grassmannian graph. Let's say N2. N is the dimension of the higher dimensional space. 2 is the subspace that you're choosing. So graph N2 is the space of all 2-dimensional affine subspaces of Rn. And for each of the subspaces, you have this cross-section with your data, and you have computed the area. So it's giving you a number. And you will try to optimize it on this Grassmannian. So, and of course, you can always give a parameterization, but some parameterizations are better than others numerically. So for example, you can associate with any, forget about affine Grassmannian, let's just talk about Grassmannian, things that pass through the origin. So Grassmannian N2. So in that case, what's the point I was trying to make? Yeah, right. So, but eventually when we try to compute, you will want to use numbers, right? You want to use matrices and numbers. So one way people do that is look at projection matrices. So any 2-dimensional subspace can be put in bijection with a projection matrix of rank 2, right? It is project, and which is essentially, what is it doing? It is taking any vector, projecting onto that 2-dimensional subspace. So when you're doing your optimization, you can use you can define this manifold using the space of 2-dimensional rank 2 projection matrices, right? But the thing is, numerically, this is very unstable. It has does not have full rank, so invertibility and all these are an issue. So when you numerically work with it, it is a problem. So typically, another strategy to do it is use reflections. So reflections are orthogonal matrices, but they carry the same information. So these are all representations in various ways. But the actual mathematical object we're dealing with is Grassmannian N2, or in this case, graph N2. So when you want to formulate something, or you want to formulate a problem, or you want to think about this problem, it is much easier to think in this decision space. When you do the computation, when you do the algorithm, you have to choose coordinate systems. It's just like difference between matrices and linear transformations. Matrices are easy to work with. You get some bunch of numbers, you multiply, computers can do it very easily, and so on. But linear transformations capture exactly what is going on, like free manner, and so on. So when you're reasoning, you like, why is matrix multiplication associative? You don't multiply numbers. You just say, okay, I'm composing just 2, 3 functions, and function composition is associative. Hence, so the arguments become much easier. That's the point I was trying to raise. And without a concrete example, I don't think it will be clear. So perhaps I'll revisit this, maybe like later down in the course. I'll revisit this, then it will be clear. So does that roughly answer, like, at least give you a feeling of why I mentioned that?
Okay, yeah.
Okay, thank you. Any other question? Okay, if not, then we will meet on Thursday, 8:55, and we will start talking about like the basics of like convex bodies in Rn, and then some basic results in linear algebra, time permitting, and so on. All right, see you then.